Okay, so I wasn't smart yesterday, so I didn't check if the sound was working, and no sound was working on the videos. So for those of you who weren't there, I'll quickly go over what we talked about yesterday. So we are continuing our study of our basic study of time series, and the last part of chapter 1 concerns something that's, well, it's not mathematically very interesting, so I won't spend much time on it, but it's an important part of the process of understanding your data set. So the idea is that when you receive your data, or when you look at it, for example, let's look at this. Where is it? Let's look at this data set. Can't find any data set here. Here, let's sorry. Let's have a look at this data set here. What do we see? Well, we see that there is clearly some kind of exponential growth, and we see that there is some kind of cyclical part. So it feels quite obvious that this data set here is not it's clearly not a stationary process, and it feels quite obvious that this guy xt is of the form something, which it would be the trend, then plus something which would be a seasonality, which then gives these waves, these regular waves around the trend, and then plus some random noise. So the whole point of much of the course will be to study this random noise, but obviously we can only study this random noise and its properties if we can use the assumption of stationarity, which is clearly not satisfied in this case. So the first step would be to identify and eliminate, or it's probably more the other way around, eliminate and identify the non-random parts, so the trend part and what could be identified as a seasonal part. Same thing here, when you look at this data set, well, clearly the mean seems to be constant, however, there is a clear swinging part. So this data set would probably be of the form xt is equal to some seasonal component plus the noise. Again, we want to study the noise. This is the interesting part which contains the intricacies of the model, but we first need to be able to understand and identify and eliminate the seasonal component. Same thing here, we clearly have some upward trend, looks more linear in this case, but we also have swinging of the behavior. Well, I'm saying it's linear, but it actually doesn't look so linear. It looks more, it looks to be becoming exponential. Oh, sorry, it's the temperature, so it's just depressing. So this guy again would be of the form something. The process is some kind of a trend and then some kind of seasonality. Clearly there are swings here, so we see that there is some kind of intrinsic seasonality which we need to get rid of, and then plus the stationary part. Okay. So this last section of the chapter is devoted to the study of how we can identify and eliminate this non-stationary part. And well, there's a variety of ways. Just one thing is that if you want, you can compute covariance and autocovariance of the process before eliminating the trend and the cyclical component, but you will be left with something which is not meaningful. This is the autocovariance of the series which was on figure 1.8. So it was the series given by the signal plus noise. So you had the signal, I forget what it was, cosine of something in terms of t, plus a noise. And obviously this guy here is not going to be stationary, and you have to eliminate this non-random part before you can do anything. And if you don't eliminate it, well, you can still compute your covariance, but it will look like something which is not at all stationary. Whereas once you eliminate this part here, you're left with the covariance, which is just the covariance of the noise, which is exactly what you expect. So it's something at lag 0 and then nothing after lag 0. Okay, so how do you eliminate these components? Well, there are a few ways. One way is to estimate them. You get an estimate, and then you get an estimate MT, well, it's written here. There's no point in redoing it. You get an estimate MT hat, you get an estimate ST hat, and then you get your data, let's say XT hat, by taking XT minus, so it shouldn't be an XT hat, it should be a Y hat. You take XT, this guy, and you subtract your estimated trend and your estimated seasonal component, and this in principle, if you've done your estimation here and here correctly, this should leave you with only the stationary part. So how do you do this? Well, there are a few ways. Maybe I'll start with the second way this time. So perhaps the most easy to set up approach is regression approach. So what you say is that you suppose that your trend is, so let's suppose that there's no seasonal component. We only have a trend part. And we suppose that our trend is some kind of linear combination of certain basis functions, typically polynomials. It could be something else. And then what you want to do is you want to eliminate this guy by estimating the coefficients. Well, one of the most natural way of estimating coefficients in such a thing is to do linear least squares regression. So you look at the difference between the observed signal at time t and the predicted signal level by your model. So you look at xt minus b0 and all this, and you find the parameters which minimize this expression. So this is just a regression. And when you do this, you're left with estimates b0, b1 to bp of your trend component. Then you can eliminate it, and you can you're left with only the stationary part of your process after this thing. So a regression approach works very easily. In R, it's pre-implemented, so it's really easy to do. So for example, here it's just the LM function in R, which you can use to regress the data over time. It's automatic, and then you can obtain your estimated trend by this technique. In general, it's also very easy. It's mathematically it's not very advanced, and it's very easy to set up. So that might be a good way to do it. Another way would be to transform your data by applying a linear filter. So here the idea is the following. Let's look at what I did here. Suppose that your trend is linear of the first order, and consider so consider the weighted average of your data xt with weights of this form. So you take weights which are non-zero only for j equals to minus 3, minus 2, minus 1, 0, 1, 2, 3. And you apply this weighting to the process. So you take the sum of the coefficient times what? Well, times the indicator. This gives you what? It gives you just the sum from minus 3 to 3 of the xt minus j's. Let's compute this. So I replace xt by what it is. I replace this here. This gives me b0, doesn't change, b1t minus j plus yt minus j. This is here. The weight can come out. There it is. And then I just take the sum. b0 times the sum of the minus 3's just gives me b0 times 7. b1 times the sum, well, that gives me something. And then I'm left with 1/7 of the sum of the yt minus j's. Okay, this guy, I'll leave him where he is. And now I look at this thing. Well, if I compute this thing, it's the sum of the t's. Well, that's just 7 times t. But 7 kills with 7, so that's b1t. And then it's the sum of the j's. But the sum of the j's is what? It's minus 3 plus minus 2 plus minus 1 plus 0 plus 1 plus 2 plus 3. Well, that gives me 0. So this sum here disappears. So I have b0 plus b1t plus nothing plus noise here. So what we see is that the linear trend, when we apply the moving average filter here, the linear trend comes out untouched. It's the phrase is, the linear trend passes the filter without distortion. There is no distortion. After the filter, we have B0 plus B1t, which remains B0 plus B1t. Whereas the signal itself will be averaged. And the idea here is to say, well, if you have your trend, where is it? MT. Suppose that you can determine weights in some kind of moving average, which leaves the trend unharmed. So after the averaging, you're left with something which is close to your trend. And suppose that you can make the rest probabilistically go to 0. So here, for example, if we generalize, rather than taking order 3, we take order Q. Well, if Q is large enough, then some law of large numbers will argue that this is necessarily close to 0. So that this estimate here actually is very close to the true quantity MT, because the true quantity is unharmed by the filter. Well, if we take our Q large enough, then this goes to 0. Therefore, by doing this, by applying the linear filter, we actually get an estimate of our trend. But once we have the estimate, we can remove it from the data, and we are supposed to be left with stationary sequence. So once we have that, so the idea is, if in general, if you can find weights which are such that the trend basically comes out without distortion, and the random parts, so the stationary component, basically comes out close to 0, well, then you can get quite good estimates of your trend, which you can then eliminate and focus. You'll be left with only the stochastic part on which to focus. So there are a few general results that you can find here. So for example, you will prove in the exercises that any polynomial trend of order k will pass through a filter aj, if and only if the sum of the weights of this filter is 1, and the linear combinations of powers of j's are all going to 0. So this is the case, for example, with the weight we have just studied. If we have 1/7 for indicator of j being less than or equal to 3, well, then the sum of the weights, the sum of these guys is indeed 1. And if I take the sum of j times 1/7 times the indicator, this gives you the sum for j going from -3 to 3 of j, and this is just 0. So this is also satisfied. Okay. So what does it look like in practice? Well, we can do this, for example, to the global temperature data. We apply a filter. In R, again, it's very easy. It's just you have to know the commands, but once you know them, it's very easy to apply. You apply the filter of 7s, and then you get this estimate of the trend. You remove from the data the trend, so this is what I do here, and you're left with the stationary part. Of course, at the end of this, you will have to test whether or not the data that you've obtained is indeed stationary, but that you will be that we will explain at a later stage in the course. And then finally, the last approach would be taking differences. So here the idea is it's very simple. It starts with the observation that if you have a seasonal component, let's say ST, and suppose that, for example, your seasonal component is quarterly, so every 4 months the procedure repeats. So you have something in June, and every month of June you have the same component. In every month of July you have the same component, and so on. Something like this. So you'd have a cyclical part. Well, in order to remove this, you could say, well, if my behavior repeats every 4 months, like this, well, if I know that it repeats every 4 months, I know that ST is equal to ST minus 4. Therefore, a good idea would be to look at the signal where I just remove from YT minus 4. Because if I do this, well, I have ST plus YT tilde, this is this guy here, minus ST minus 4 plus yt to the minus 4. Well, these guys simplify. They kill each other because of the seasonality assumption. And I'm left with some noise which now would be stationary. So therefore, taking finite differences, so it's called a discrete differential, taking these finite differences of order 4 will kill any quarterly seasonal component. To do this in all generality, we define the backshift operator, which sends a discrete function to just the discrete value at time, just b of xt is xt minus 1, and bk of xt is xt minus k. And you will be showing in the exercises that you have certain form of calculus on these backshift operators. So you will be proving propositions. So you will be proving that these statements are correct, and you will also be proving this proposition in the exercises, and I will let you do that. Voila, so that's the end of the first part of the course. I will stop the video and start a new one.